Hey everyone, welcome to another deep dive video with me and Erik. And this week we're looking at the Pangram exercise. A pangram is any sentence that uses every letter in the alphabet at least once. And in this video we're going to be looking at a variety of different solutions. We've got some things that use strings and regular expressions. We've got a bit of higher order functions. We've got some set theory. We've got some bit shifting. Really interesting, different selection of ways to solve what is a relatively straightforward exercise, but it's always fun to see all the different approaches you can take and get a bit inspired. We're going to be looking at a whole set of different languages as well. So it's going to be a fun video. I'm joined by Erik as always, and we're going to dive straight in, and we're going to be looking at this solution in Kotlin. Erik, take us away. Tell us what's going on here.
Yeah, so this is Kotlin where you have a single function takes in a string and returns a boolean. That makes sense considering the exercise. There are a couple of things that are being used here. On the left side, you see A between the single quotes, which is the character A, dot, and then you have Z between the single quotes. That is the range of characters from A to Z. Mm-hmm. So if you have been using regular expressions, for example, you'll know that you have ranges where you start with a letter and you end with a letter. Mm-hmm. So this basically is the entirety of the alphabet. Mm-hmm. Then there's a call, so it's also an object. So you can call .all, and .all is a function that takes another function that it will execute for every single one of the elements in the collection, mm-hmm. and it will only be returning true if all of those individual elements that function return true for them too. Mm-hmm. So in this case, what we're doing is we're checking every single letter. Which is it. So that's Kotlin syntax for, this is shorthand syntax basically. So mm-hmm. that's the element that is being worked on. And it says, hey, if the input string contains that letter, mm-hmm. but ignore the casing because we don't care about lowercase a or uppercase a. They're both counting as an A. Mm-hmm. So, and we're checking if it contains that character, then we return true. Otherwise, mm-hmm. we return false. So we're basically saying this is very literal how the exercise is specified. Mm-hmm. All the letters of the alphabet must be in the input string. Mm-hmm. So this is not necessarily efficient mm-hmm. because every single call will do the contains bit. So that might be traversing the entirety of the string, or at least a lot of characters. Mm-hmm. But it is very easy to read, and it does represent the domain. So the exercise well, I think. Mm-hmm.
Yeah, one of the sort of characteristics of this exercise is there's some really readable solutions, and we'll see solutions later. Julia one, for example, that's remarkably readable. And there are ones that are probably very, very performant as well. Some that will be performant in terms of memory usage, some that will be performant in terms of CPU usage. But I feel like one of the interesting things in this exercise is the trade-offs between these different, readability versus performance, etc. So yeah, it's interesting to think about when we've got sort of these higher order functions and loops and things, how many times are we having to pass the data? What does it mean for us to ignore the case? Does that mean we're having to check everything twice? And it's also interesting to see this range here. I know a lot of languages have this sort of range syntax. Is it pretty ubiquitous now, Erik? Would we find that in nearly all languages, or is it still a sort of subset of languages?
I think most of the modern languages will have some range syntax. Sometimes it's backported to all the languages too. Mm-hmm. Sometimes in ways that are not as what you might have expected. Mm-hmm. I'm talking about C#, but most of the modern language will have something like this. Mm-hmm. Ranges are becoming more and more familiar. Thing.
Okay. Nice. Okay, let's jump forward to the next solution, and we're jumping into Python. Go for it, Erik.
It's a very similar solution. As a matter of fact, the function name or the method name in Kotlin is the same. It's all. Mm-hmm. So again, we're doing something where we want to validate everything's being true. Mm-hmm. The difference here is that we're not using a range. We're importing ASCII lowercase mm-hmm. from the string module. And that's a predefined thing. And it's one thing that I often, when you do exercism exercise, you have to use this a lot. Mm. You often work with ASCII. You have Pangram, but also isogram, and there's a lot of grams. Mm-hmm. But I always find it confusing that many languages don't have like a definition of the
Yeah.
ASCII lowercase. I know Ruby does, for example, and there are more languages that do, but there are a lot of languages that don't actually.
Yeah.
But Python, of course, is one of them that does. So the way that you should read this is you actually go from right to left. So you start with for C in ASCII lowercase. So these are all the letters in the alphabet, lowercase letters. And then we're doing, for every single one of the letters, we're doing C in s.lower. So we're checking if that letter is in the lowercase version of the input string. And that gives us a Boolean. And then all those values are basically passed to all. So if every one of those were true, then it will be fine. If one or more of them were false, then the result will be false. And again, this is very readable, but you're doing a to lower case conversion every single for every single letter. So you're doing this 26 times, which is not necessarily very efficient. But it is very readable.
Yeah, although I do find the sort of double in here confusing at a glance. I know that this is, how Python does things, and list comprehensions and things can be really nice, but I do sort of find, like, not knowing just instinctively with any syntax that this is sort of the left-hand side and this is the right-hand side. A little tricky when I'm just glancing at this, but yeah, it's perfectly readable. And the more you use Python, the more this will be familiar. Okay, so JQ. This is a really nice, fun one, Erik. And this is sort of a slightly different way of doing things, isn't it? It looks very, very functional.
It is.
Yeah, talk us through it.
This is a perfect example of a pure functional pipeline. So you start with the sentence, then you pipe that into ASCII downcase, which of course lowercase is the string. Then you do explode. Explode means converting the string into its individual characters. And then piping that into unique, which removes all the duplicates and also sorts it. And that's something that we're going to use later on. So basically, we're removing all the duplicates and we're sorting them. That's how you should be reading unique. And then you put them back together. So you do implode. So it's a string again. And then we pipe it into contains. And we're basically checking if the entire alphabet is contained in that string. And because the letters are sorted and deduplicated, then if the alphabet was in there, then that string must be in the input string. So
nice. And we don't use a straight comparison because you're also allowed numbers in the strings as well, aren't you? So you're saying you might have the numbers at the start, I guess, and then maybe some punctuation at the end or whatever. But at some point, there will just be this alphabetical block in the string that we can look to. Yeah, that's really cool. It's a really nice, neat solution, that, isn't it? Yeah, nice. Okay. My solution to Ruby, Erik. I'll let you talk through it again. I know you love talking through my solutions.
I do. So, well, we're downcasing at the beginning. So that's one of the things that we're doing here. So we don't have the downcasing shenanigans going on. Then we're doing scan. So this is a regular expression. And we're seeing the range A to Z like we had with Kotlin. So these are all, this basically gives us a new sequence of all the letters that are, well, the lowercase letters, which are the only letters here because we did downcase. Then we're doing .unique. So we get a new sequence, a new list of elements, but just the unique ones. And then we can count them. So if we have all the letters in the alphabet, then that should be 26. So that's what we're being done here. So we're getting all the letters. We're removing any duplicates, and then we're counting them, and there should be 26. And if there are 26, all the letters in the alphabet are in the string.
Yeah, a nice simple way of avoiding having to do the string comparison bit, which is sort of why I like the count approach. And also, you're just sort of doing each thing once as well. Again, it's sort of a bit of a functional approach.
Yeah, very.
Although, ironically, it's all methods. So it's the weirdness of Ruby where you tend to get things that feel quite functional, but actually they're all just methods acting on objects.
But they are returning new values, so they're not mutating. So that's quite functional.
Yeah. Okay, cool. I don't think there's much more to say about that. One thing I would say with the scan is it's nice that scan breaks that up into an array. Originally, when I did this, I filtered it and then got the characters out. but scan's a nice little shortcut for just pulling those things out. One thing as well that I sort of am always surprised about is that I don't know at least of a lower, like a shortcut in regexes just for lowercase letters. There might be one, but there's obviously like word characters and other things, but
I know for certain that there is a lowercase Unicode letter
yeah,
one, but I'm not sure if there's a lowercase ASCII one.
yeah,
because that's what we on. We don't want to mention like other alphabet letters.
no, not in this.
At least not in this exercise.
Yeah, exactly. Okay, cool. So now we move on to a very different sort of approach. This is Lua. Yeah, talk us through this, Erik.
Yeah, so this is a dictionary/map based approach, although it's called tables in Lua. And so we have a table, and that contains a field size, which starts at 26, and you probably can guess that's how many letters there are left to match. And then for every single letter, we assign it the value true. So, then obviously we have to do something with it. We just mentioned regexes, and actually Lua does have %L, so that's letter, but it's not a lowercase letter per se, because we're doing lower first. But I find it always interesting that Lua has its own regular expression flavor, I would say. So basically finding all the letters, and we're looping over them in a for loop. And then within the for loop comes the real meat of this implementation. So we're checking if when we index into letter tab, which is that whole big table/dictionary with the character, if we find something, so that was true, and that will only be true for one of the letters, then we are setting it to nil, so that next time we won't be processing it again. We decrement the size element, so that's basically our count of how many letters we haven't yet seen. And then on line 13 comes where a little bit of performance optimization. So we're checking if the size, so how many letters we've not yet seen, is 0, which means that we've seen them all, and then we can return true, because we don't need to continue. We have already seen all the letters. So this is really efficient if you have a very, very long string. So I don't know, if you have the alphabet repeated like 1 million times, this would just iterate over the first 26 characters and then would stop.
Nice.
So if you wouldn't do this, many of the other solutions would just keep on trying. But this one is short circuiting, so that's quite efficient.
Yeah, nice. It reminds me a little bit of the Civ video we did recently. I can't remember how to pronounce the philosopher's name, but do you remember the Civ of
Aristosthenes?
Aristosthenes, which is a totally different algorithm, but it's for finding prime numbers, but where you're sort of ticking numbers off as you go. You write all the numbers down and then tick them off. And it's sort of the same approach here. You know, you start off with all of the letters written down and then cross them off. Is it normal to have sort of this different arbitrary variable inside this table like this in Lua? It seems just instinctively a bit odd to me to have all the letters, but then this.
I don't think it's necessarily idiomatic Lua, but it might be. I'm not a big Lua not expert, but the other solution that I saw, most of them didn't do it like this. So you could just as easily have a second variable that was just size, but I don't know. Yeah, just options, I guess.
Yeah, for sure. Cool. Okay. A sort of unexpected solution in a way. It's not an approach that I thought to take, but as you say, it makes a lot of sense. Yeah, nice. So moving on to NIM, this is, I guess, a similar approach, Erik. Is this your solution to NIM, or is this one you've copied off someone else?
No, this was adapted from somebody else's.
Okay.
Yeah.
Talk us through it.
Just for readability purposes.
Yeah.
So now we're moving into, we just had a dictionary, which is which has a relation with the set, but we're now moving into set territory, and a set is basically a data structure that can't have duplicates. So that's perfect for our use case, because we are not interested in the duplicates of the letters, just in the fact of whether or not a letter has been seen. So on line 5, we're initializing a hash set of characters, and we're giving it an initial size. And we can do this because we know there will never be more than 26 elements in that hash set. So This is just a tiny optimization. It might not even matter, but it's sort of, you're making it explicit that you already know beforehand how many elements that can be in the hash set. Then we have basically a combination of things that we've seen before. So we're doing the to lower to start with, and then we're looping over all the characters in that. And then within the loop, we're checking if C is in lowercase letters, and that's similar to what the Python solution did, where nim provides you with a predefined constant value. So lowercase letters is not defined by this solution; it's defined in strut utils. So that module, and we're then checking if we've not yet seen that letter. So this is a lowercase letter that we haven't yet seen. Then we do on line 9, we say .include, which is stands for include. So we add it to the set, and we check whether or not we have 26 letters. So there isn't the count of letters. So I sort of like that in its lowercase letters .length. So you don't have the magic 26 number here. Although it's very weird to have more lowercase letters in a couple of years or something like that.
Yeah.
But this is short circuiting, and and the lines below will be like return false, because then if we get there, we won't have seen all the elements.
The one thing I'd say about this is the fact that we're checking whether it's in letters sort of means that it doesn't really matter whether this is a set or not. This could just be a normal hash table.
And that check could even be removed. That wouldn't really be.
Yeah, this is just an optimization, isn't it?
Yeah.
Yeah, nice. Okay, cool. Then moving on to Pharo. This looks, I always find Pharo challenging to read at a glance. But talk us through it, Erik.
So I found Pharo challenging to read at first too, but I've come to love it. So maybe others will do too. So I would recommend you to at least try out Pharo, because it is very different. You can forget about most of it. It's somewhat boilerplatey, but that line where you have, that's the key line. So the hex sign means return the value after this character. So we have a couple of things going on. So we have character, alphabet, and alphabet is a message that is being sent to the character class. So it's like a method, but it's actually a message. And that will return, well, the alphabet, of course. And then what we do is we're calling on that alphabet, we call the method, or we send the message, difference. So difference is set difference. And the argument to that message is the input string as lowercase. So the idea here is that you have two sets. You have the alphabet, and you have your input string lowercase. And the set difference is all the elements in the first set, except for those that are not, well, let me put that better. So all the elements in the first set that are not in the second set. So, but if all the elements are in the actual string, it will be empty. So they're basically overlapping, and you do the difference, and means that you don't get the overlapping bits, you get the other bits, which means that in the case of the alphabet, if it is empty, all the letters of the alphabet are in the string, and you're done.
So this is a one-way set comparison. So we're saying we've got everything here, and it does everything here also exist in here effectively, but it doesn't work the other way around.
You could see this as give me all the elements in the leftmost thingy that are not in the rightmost thingy.
Yeah. Okay. Yeah, that makes sense.
That was very scientific of mine.
Yeah. Nice. Okay, we're going to look at some more, another set one here. This is by far the most elegant solution. I know that you love this. This is basically what we've just seen, isn't it, Erik?
Yeah, I think this is, how much better can it get? This is just, there's almost no boilerplate here. It's just a function is Pangram between parentheses as equals. Then we have a range, A to Z, same like that we did with Kotlin. There are usually two different ways in which tracks implement ranges. Either they do ... or even ... or they do colon. And Julia has chosen colon. And then there's that weird math symbol that you might not be familiar with. And that basically says it's a subset. So, and that means that what we just explained on for Pharo, if the leftmost part is in everything that's in the rightmost part, but it's not using the difference. It's using
Mhm.
this subset.
Mhm.
So this can also be optimized. So
Mhm.
this should just be read as everything in the left should be in the right.
Mhm.
And then the fact that it's characters and the right is a string, Julia will handle that all for
Mhm.
you. But it's just a very elegant way of saying, hey, everything on the left must be a part of the right. And you don't care about ordering or whatever or duplicates. Just every single one of the values has to be in the right value. And that's it. That is what the definition is of the exercise too. But
Yeah. That's I always like solutions that are that. It's if the code reads the same as the description we've written, I always think that's a really nice way of doing it. Do you think difference here is also implemented as a subset under the hood? Because it is just the same. Like this line of code is identical, right?
well, subset is the Julia version gives just a Boolean.
Okay, so it's true or
whereas
false.
whereas
Right.
difference gives you actually a new set.
Okay,
There might also be something like subset, but
Mhm.
in Pharo it probably is.
Yeah.
But they're they are linked, but they're not
Mhm.
the same.
But they're a bit different. Okay, understood. Okay, so then moving on to Rust, everyone's favorite language to feature in these videos. And here, I'm guessing we're moving into bit shifting territory here, Erik.
Yeah. So the key thing here to behind this solution is that we want to keep track of 26 things, whether or not we've seen them or not.
Okay.
And 26 values could be 26 bits. So either it's a 0 for I haven't yet seen it, or a 1 for I have seen it.
Okay.
And well, you have 32-bit integers. So 32-bit integers are enough to keep track of all those 26 characters. So that's why we have U32. So that's basically the default. The default is probably a signed version. This is an unsigned version. But as long as it's 32 bits, we can keep track of all the letters. So that's what we're going to do. So we're going to return to that magic number later on.
Okay.
We're going to start at line 9, where we define a mutable value letter flags. So this will be our integer, where initially every single bit is 0. So that means the value is 0. And so all the bits are 0. And then within, we're going to loop over the sentence. So over all the characters in the sentence. And then we're going to do, we're going to compare characters to, well, this is sort of like a range, but it's just written a little bit differently.
Yeah.
So if the letter is greater or equal to lowercase a and less than or equal to the lowercase z, then it is a lowercase character. And then we have to we found a letter. So that's great. But we now have to sort of mark it in our 32-bit number. So we have to give it an index. And we can't just use the letter value, because a lowercase a value would be 97. And a 32-bit number doesn't have index 97. So basically what we're going to do is we're going to sort of start at 97. So we're going to do letter minus 97. So it means that an A will become a 0, a B will become a 1, etc., etc. And then you have that 1 and then 2 arrows pointing to the left. So that means 1 shifted to the left the number of times where, like the letter index. So the letter A has index 0. So that means 1 shifted to the left 0 times means 1. So that will be the rightmost bit.
Yeah.
So we then have to set it. So if you want to set a bit, you're doing a bitwise OR. And this is basically the same as letter flags equals letter flags OR. So this is a shorthand syntax for it. But we're basically saying that index of that letter, we're flipping that bit to 1. Although theoretically, if it is already 1, it will stay 1. We don't check for that. So we're ensuring that it is 1. Let's keep it at that.
Just to be clear, we've all got this. So if we've got a long set of bits, and we're starting at the rightmost one.
Yeah.
If we see a letter A, we flip the rightmost bit from 0 to 1.
Yeah.
If we see a letter Z, we flip the leftmost bit from 0 to 1.
Well, not the leftmost bit, but because the leftmost bit will be index 32.
Yeah,
well,
okay,
31.
so the 26th one.
Yeah.
Right? Yeah, 26th bit. and then all of the other ones, accordingly in between then.
Yeah.
And then we're doing the same with capitals, but
Yeah.
using 65 instead.
Yeah, and we're basically we're ignoring duplicates. We're setting, if it was a duplicate, then we just try and set it to 1 again, but it was already 1, which is fine. And we don't do short circuiting here, so we're just looping over everything. So that might have been an optimization actually, as we're trying to get as optimal as we can. But in the end, what we're going to do is we're going to compare to the very well-named all 26 bits set. So that's that magic number. It's just a number where the rightmost 26 bits are all 1. And only when all those bits are 1 have we seen all of the letters. So that's the result of the of this function.
This could, I presume, have been written out as 0.0.0.0.1 as well, with some sort of slash in front of it.
Yeah, totally. And you could do probably, I don't know if Rust has binary notation. It probably does.
Yeah, I'm sure
it would be 0, B, and then a lot of 1s. But
but Bob's showing off with his knowledge of binary to.
But it is well named. So.
It is well named. Yeah. Nice. Okay, this is a cool solution. I like this. Very clever. And then this is just some benchmarking stuff at the top, I'm guessing.
Although micro optimization would be to return early, so moving that letter flags into the loop. But maybe that would be it all depends. It depends on the actual.
You almost want to have 2 algorithms, don't you? If it's less than 50 characters, you want to go with one way, and if the string's more than 50 characters, you might want to go a different way. There'll be some sweet spot of that somewhere. How do you think this performance would compare to the other ones we've seen so far, instinctively, say compared to the Julia one?
The Julia one is hard to estimate what they do under the hood. So I don't. For example, the set difference one, the Pharo one, and it's not a mark on Pharo, it's just on my solution. Because set difference returns something else. So there is like bookkeeping, and you have to do a lot of management around it. So this is very memory optimal.
Yeah, this is as optimal memory-wise as you can get, probably,
so
isn't it?
You don't have 26-bit integers, but this is, I don't think you can get can do much better memory-wise. Performance-wise, there might be tricks that you can use. For example, to we did it in a previous video where there was a trick to convert an uppercase character to a lowercase character. And then you don't have that you could have less branching then. You could do a bit of bit fiddling, but that wouldn't be as clear as this. So there's probably a couple of minor tricks that you could use,
or even just the downcasing. Again, on a short string would probably be quite fast. Maybe faster than the 2 comparisons, but
could be.
But then maybe not. I don't know. Yeah. Okay, one more solution to look at. This is, I guess, pretty similar. Looking at this integer bit set, but we're in Zig here.
Yeah, we're in the Zig territory, so it's always interesting to see that the string is represented as a slice of bytes, so unsigned bytes. So you don't have a string type per se. And then what Bob did is basically such a common pattern that many languages have a built-in data structure that implemented like that. And in Zig, that's called an integer bit set, which is very well named. Again, we have to give it a capacity, and that is not just for nothing. I'm not entirely sure if the integer bit set is like. I know you have data types where you create them, and it will specialize depending on how big it is. So if it is 26, then you can fit it in an integer. But if it is like 7, you could fit it in a byte. So under the hood, there might be different representations of the actual the backend side. So it would be wasteful to allocate a 32 bits when you only need 8 or 7. But I'm not sure that's what they do. But that's often why you have these sort of wrapper-like function calls to create a data structure, and under the hood there might be something that's actually happening there. Well, then init empty basically sets everything to 0 at first. And then, well, there's a for loop. We're checking if it's alphabetic. And then we're doing continue if it's not. So we're going to skip over everything that's not a letter. So that reduces indentation, which I always like. And then the letter is converted to lowercase. So that could also be a micro optimization where you could convert the entire string to lower, but that would have to traverse all the letters in the alphabet, all the letters in the string. But in this case, we're only doing it for letters, which is the only thing that we are really interested in. I'm not sure what would be faster. That could be depending on the input, of course. But then we do -a, which is the same trick that we did before. So it means that the lowercase a minus lowercase a is 0, b minus a is 1, etc., etc. So, but this time we're setting it based on the index value. So we don't have to do any bit twiddling here. So we don't have shifting. We don't have a bitwise OR. That is all being implemented by the data structure itself. So that's being handled for us under the hood. And in the end, we can just count, which means check how many of the bits are set to 1.
Yeah, nice.
And then we check if that's 26.
Yeah. Very cool. It's a nice solution. I was just thinking as you were talking about, this being an optimization of moving this above. I guess it very much depends how you're actually implementing this, because if you're implementing lowercasing a string by just going through every letter and lowercasing the letter, it probably does make no difference as to whether you do that on the whole string or just on a single character later on. I guess there's a question of, is there some sort of better optimization if you're working across a whole string? Maybe you can parallelize that or something else. But yeah, I don't know if there is a better optimization that most languages would use. Yeah. Okay, cool. That's the end of our solutions. Any sort of final thoughts you have on the exercise or on any of those solutions, Erik, as we've seen them as a whole group now?
No, I think this is a typical solution where you can start out with actually quite a lot of code.
Yeah.
And then when you start digging around a little bit and you see what other people have done, that you notice like, hey, there are lots of ways in which you can replace my code with something that might be more elegant.
Yeah.
And for this integer bit set type, you can check if your language has it. I know C# has one. I think Java has one too. A lot of languages do. So you can check if your language has set support. So I think almost all languages have some type of set, not all language, but even JavaScript has it. So that means that probably a lot of languages do. So I would just encourage you to experiment because it's a fun little exercise. It's not too big.
It's one of these exercises, I think, that lots of people's solutions end up coalescing on a smaller set of solutions. I didn't look like, I'm sort of amazed that there's only been 2 people have submitted this in Julia using this exact solution, because I imagine when you start looking at Julia solutions, the moment you see this, you sort of want to almost update your solution to that. But yeah, some solutions you end up with a very dispersed, wide solution space, and other exercises you end up with a lot of people look at community solutions and then get inspired and sort of update their solution. And yeah, this is one of those exercises where I think that's the case, exactly like you're saying. You start off in a more verbose way and then come down. But I do think choosing which way to optimize, be it memory or CPU or readability, is really fascinating as well in this one. And probably showcases different languages a bit as well.
Yeah, if people have benchmarks that they've done, maybe micro optimization that we haven't thought about.
Yeah,
and please let us know in the comments.
It's really always great.
Interested in reading about it.
It would also be good. I'd be really interested to see an assembly solution here as well. So if anyone watching this has solved it in assembly and or wants to go and solve it in assembly and come back and link in the comments of this video, it'd be good to see an assembly one for this as well, because I imagine that could be really interestingly optimized. Cool. Thanks, Erik, for finding the solutions and talking us through them. Thanks, everyone, for watching. And we'll see you in the next one of these videos. Have a great day.